Okay, so today is the last lecture, and the plan is I want to do one more application of the Joyau's theorem, and this I will do with all the proofs, but then I'll have something like probably 40 minutes, and then I'll formulate several things and just do statements without proofs, just to give you some additional information, what's important in this theory that we wasn't able to cover in these lectures. So I'm not sure what this section is. This is, look at this, this is 4.5, maybe 6. So I'm going to call this invertible natural transformations. And essentially, if you look at the theory of just one categories, there is a completely silly observation. There's a natural transformation is invertible if and only if every component of this natural transformation is invertible. Right? This is usually taken as a definition even, but even if you take this as an equivalent condition, the proof is completely trivial. So in this case, this is not trivial at all. It relies on the Joyau's lifting theorem. So let me maybe just briefly remind you what you already know. So in the second assignment, I think, and it follows from the result from the lecture quite easily, that we have the observation that if you take inner vibrations to the box mono, then this is again an inner vibration, right? And the special case of this statement will be the following. You can look at the, say, map. So this implies that if you look at the following situation, you look at the fun from some simplicial set K to some infinity category, and then and then you restrict this to the fun, and you take K0, so the vertices of the K, right? So I claim that this is inner vibration. So this is inner vibration. Of course, the assumption is here that C is an infinity category. OK is any simplicial set. Right? No, because this is just a pullback home, right? So this map is a special case of a pullback home when instead of having some kind of map from infinity category from C to D, you just take the map from C to the point. This is kind of special case of the pullback home. And of course, this cell that we have here, all right, so maybe it's not completely clear. So here, or maybe where, so I, that is a monomorphism in this case, is just an inclusion of the K0 into K, and this inner vibration, this is just a map from C to the point, so that's an inner vibration, since I assume that C is infinity category. So this will be a special case of a pullback home for these two maps, so special case of this general statement. So we know that this is an inner vibration. Just a simple observation, just to remind you. I'm going to use this in a minute. So in the next definition, essentially. So definition. So this will be kind of temporary definition. So we define what I'm going to call map with a large M. So this will be kind of subset of the functors from K to C, which is defined in the following way. So I'm continuing to assume that C is infinity category, K is simplicial set. So I'm not going to write this again. So as the pullback. So here's the pullback. So the map from large K to the infinity category C, this is a pullback of the following diagram. So you take fun K0 to the C, and then you take the core of this infinity category. This is included, of course, as any core to the fun from K0 to C. Right? So this is just an inclusion of the core. And the second map, this is the map that I just discussed. So this is from fun K, C. So clearly you have two such maps, and you take a pullback of two such maps, you get the pullback diagram in the category of simplicial sets. Well, that's the definition. Well, what we can immediately see from this definition, for example, for example, since this map, as I just discussed, so this map here is an inner fibration, and inner fibrations are closed under pullbacks. Well, we immediately know, I don't want to rewrite this map, so I'm just write it like this. So that this is again an inner fibration, right? As a pullback of an inner fibration. And then we can also notice, so note that map that I just defined, this is an infinity category. Right? Well, since this is an inner fibration and this is a Kan complex, right, as any group, maximal subgroupoid is, and we know there's a general property which can, actually this is completely trivial, right? So since this is a Kan complex, this is an infinity category, right? So there's this canonical map to the point here is a inner fibration, right? So here we get the composition. So the map from the point, from this space to the point is again an inner fibrations composition of two inner fibrations. So that's an infinity category. Okay. So then what I want to do, I want to kind of take this formal definition with the pullback and just rewrite in words what it means. So the map KC is an infinity category of functors say f from K to the C with natural transformations such that, natural transformations, let's say f to the G, so such that this is if you look at what it's doing, on every fixed vertex, so from f of k to the g of k, right? So this is an isomorphism. It's an isomorphism, and that is true for any little k which is a vertex in the k. So this is in the k0, right? So this is, if you just kind of look at how we compute pullbacks in this category, right? So this is just map here, that coincide here. So that's exactly, the criteria that I promised you is that you can check invertibility by looking at all the components. So this is exactly such functors from K to C, such that all the components of natural transformations in this category are invertible. So what we can say immediately, that the map KC, this is something inside fun KC, and then we take an infinite groupoid. So, and the goal, if I want this kind of component-wise criterion for natural transformation being invertible, I need to show that actually these two simplicial sets coincide. So we always automatically, just from definition, have an inclusion. And the goal is to show that they coincide. And in fact, we will prove something a little bit more interesting, more general than this. And this will be just one of the corollaries of that general statement. Okay, but I start with one more combinatorial proposition. No, the proof is combinatorial. So on this. Well, just because of this interpretation, right? So objects here are functors, objects here are functors, right? So here you assume that in kind of for every component you have well, you have a kind of isomorphisms, right? And here you assume that kind of all the maps, all the natural transformations here are isomorphisms, right? So if you, what do I need to say next? Just a second, I confused myself. So if yes, I'm trying to say why this is clear. Just a second. So maybe there's something missing. Maybe I need also to verify this. No, this is definitely something very easy. I just kind of don't see immediately the reason. So if you know that. Yeah, for example, I think you can look at this diagram, right? So here, this map that I just wait.
ядро отображается по универсальному свойству функции, потому что оно вкладывается в функции и отображается в ядро конвертации.
But no, but this will be a map in the other direction.
Да.
So maybe you're saying that it's obvious if I just do in the other direction. Yeah. So yeah, this is just a silly mistake. Okay. Okay. So, but before I can do this, I'll just need to do a combinatorial statement. So in this statement, let me assume that C is in some infinity category. And then I look at the functor, so functor from the delta 1 C to the boundary, so functor, and I take boundary of the delta 1 to the C. Right, so this is just a restriction for the first argument, and of course this I can identify with the product of C and C. So this functor is conservative. Okay. So to say that the functor is conservative, well, I already kind of used this argument, so let me say it like this. It suffices to show that any lifting problem is the following. I take the Horn lambda to 0. This is included into the delta 2. So then, kind of a little bit informally, since this is just a horn, it is completely specified by the two edges. So on one edge I take some map F, on the other edge I take the identity. So this will be to the fun delta 1C, to the fun boundary of the delta 1 and then C. Right, so I need to show, so it suffices to show that any lifting problem of this kind has a solution. So any lifting problem with F an isomorphism has a solution. Right? Why this is the case? Well, you can go back to the proof why, for example, any left vibration was a conservative. I exactly used the lifting problems like this with this property. So I don't want to repeat the argument. So the argument was essentially like this: if you know that you have a solution for this F, you can construct the left inverse. Then you again this left inverse. So with an isomorphism. So this is the isomorphism. In fun boundary delta 1C here. Right, so it will be some map here, so it will be mapped to the two maps here, so actually it will be two maps in the C, and these two maps has to be isomorphisms. Right, so again, the idea was you using this existence of this solution of this lifting problem, you construct the left inverse for the F. This left inverse again satisfies this property, isomorphism here. So again, for this left inverse, there is another left inverse. So this left inverse that I constructed has left inverse and also has a right inverse, which is F. Well, that's an argument that was used when I proved that the left vibrations are conservative. So I want to use it again here. Okay. So then, of course, I look at this lifting problem. Well, maybe just for convenience, I notice that I can take this fun from the boundary of the delta 1 and C, and I identify this with the fun of the boundary of the delta 1 C, and then I take product of the fun boundary delta 1 delta 0, and then there will be a fun delta 1 delta 0. So this is just a trivial way to rewrite this, and then I can immediately see what would be the adjoint problem, since I have the structure of the pullback in this corner. So this will be, so let me say that this is maybe a star. So lifting problem star is adjoint to the following lifting problem. So here I have a horn lambda to 0, product with delta 1. So this is the first argument of the coproduct over lambda to 0. Product is the boundary of the delta 1. And the second argument of this coproduct is the delta 2. Product is the boundary of lambda 1. So then this is mapped to C. This is just star, and here we have the cylinder delta 2 delta 1, so this prism. Okay, so that's the adjoint problem. We actually have seen such problems before, right? When we were discussing, for example, the very first combinatorial Giles lemma, there was something like this, but then in that problem, this set was a little bit different, and also we need to solve that problem for the cylinder for any delta n, not just delta 2. So here this is nice because this is very simple, right? This is just one particular problem which you can draw everything in the three-dimensional space and see why it has a solution. But also before I show that there is a solution, I also know that here I have this additional property that this map F in this fun delta 1C, this is supposed to represent an isomorphism after I project to the product of C and C. So if you go back adjoint data between the two, this data of these lifting problems, how they adjoin to each other, you can notice the following. So this kind of I'm leaving you as a little exercise to check that the condition that F is sent to an isomorphism in the first lifting problem, so namely in the fun boundary of the delta 1 and C, so implies that the edge, so now since I'm kind of working with this prism, so maybe I just draw prism first. So I have this, then you can kind of see everything on the picture. So, and also diagonals. So with the standard numbering of the vertices. So since everything happens inside this prism, and you can identify, so this set that we start with, this is just something inside this prism, right? So, well, for example, in the first factor, well, you take this horn, right? So first factor give you, for example, all these faces, faces, except this face that is across this edge 0, 0, 1, 0. And then the second factor in this augmented coproduct, then you get just this top face and this bottom face. So what's missing in this set here, right, is the interior, of course, and the face that is kind of in this picture on the right, and kind of on the right at the back of the picture. So that is not what we have in this set. Right, and let me just finish this sentence about the F. So now I can say that the edge delta 0, 0, right now this is just a vertex in this simplicial set, and 0, 1, this is another vertex in this simplicial set. So you kind of you take this cylinder, well, supposed to be mapped to the C, and under this map, this edge is sent to some isomorphism in the C. So implies that the edge is an isomorphism. Okay, and then I just look at this lifting problem, and I say, so we solve the lifting problem in, I don't know, so I have 4 steps and 4 steps. 4 steps. So, and the first 3 steps will be completely trivial. So here, let me again call this thing, not to rewrite this as in the previous combinatorial problem like this, I'm going to call this K. Right, so in the first step, I'm going to, from the K to the K to which I glue 2 simplex. I'm going to call this sigma, right, sigma, and the sigma will be 2 simplex with the following vertices. So this will be 0, 1, 0, 2, and 1, 2. Right, so 0, 1, 0, 2, and 1, 2. So this triangle, which is on the face, which is at the back, and on the right, which is the missing face. So now, if I glue this simplex, kind of I only have half of this missing face. And also, we can notice that when I glue this simplex to the K, so sigma is attached along an inner horn. right? Because I attach this with the horn that corresponds to the 0, 1, 0, 2, 1, 2. So this horn is already kind of part of the picture, so what's missing is just this two-dimensional simplex and this one-dimensional simplex. So since I attach this along the inner horn, right, I immediately can say that, oh, well, let me call this map, maybe now I'm going to call this map sigma 0, right? So the sigma 0 is defined on this simplicial set as a map to the C. But then I can construct, immediately get, so there is map, say, sigma 1, and this will be from the K union with the sigma to the C, right? I can extend this map to the K, which is with attached sigma, right? Because on this inner horn, the map is already given, C is an infinity category. I can extend this to this whole two-dimensional simplex just by using the property that C is infinity category. Okay, so this is the only two-dimensional simplex that I want to glue. Now I want to glue several three-dimensional simplexes, just in kind of standard way to glue the this whole prism from the two-dimensional simplexes. So on the second step, I consider maybe I want to call this something. So let me maybe call this, not to repeat this long union. So this will be, say, I don't know, x1, I think I want to call this. Yeah, let's call this x1. So this is x1 by definition. So on the next step, I take this x1 and glue to this x1 now two-dimensional simplex, which I'm going to call tau 1. So tau 1 is a simplex with the vertices 0, 0, 0, 1, 0, 2, and 1, 2. Right, so that's a two-dimensional simplex. So let's see, 0, 0, 0, 1, 0, 2. So this is kind of, if you remember when we discussed the previous such gluing problem, that's exactly the same two-dimensional simplex. Right, so now I can do this because already on the previous step I had this simplex sigma 1. Right, and again, when I glue this simplex tau 1 to the x1, I can use the same logic, right? So I don't want to rewrite the sentence, but maybe I just hope that you understand this, right? So when I glue this, it is glued along the horn that corresponds to the vertex 0, 2, right? So what's missing is exactly this face, 0, 0, 1, 2, 0, 1. And this is an inner horn. So I can use again the same logic. Since this is an inner horn, on this horn already the map is defined from the previous step, and then I can extend this map and claim that there is a map sigma 2 from the x2 to the C, again using just that C is an infinity category. Okay, so in exactly the same way as in the step 2, you just glue one more. Yeah, so again I forget to define what x2 is. x2 is just the x1 with the glued tau 1. So now I will say that there is x3, which is x2 union with tau 2. Tau 2 now in this situation is again standard two-dimensional simplex with vertices 0, 0, 1, 0, 1, 1, and 1, 2. So the same logic applies if you just find this simplex on the picture. This is again glued along the inner horn, and I can extend this map sigma 2, get map sigma 3 from the x3 to the C. So far it was just using the fact that I have an infinity category, and finally I need to glue the last two-dimensional simplex and extend the map on this simplex. So this is why I need Giles theorem. So this is last step, step 4. So x4 will be x3 with attached simplex tau 3, and you can notice that this is exactly product of the tau of the delta 2 and delta 1. So here tau 3, as you can guess already from the picture, this is 0, 0, 0, 1, 1, 1, 1, 2. Right? So let's see. 0, 0, 0, 1, yes, 1, 1, and 1, 2. So, and this is, if you kind of look at this simplex, you'll see that you glue along the horn kind of corresponds to this vertex 0, 0, right? So the missing phase in this horn is this phase 0, 1, 1, 2, 1, 1. And this is the left horn. So the horn kind of with this vertex is the left horn. So tau 3 is attached along the left horn. So now I'm using this observation about the map F. So F is an isomorphism, and this is the left horn. So the conclusion is by Giles extension theorem, there is a map which I'm just going to call sigma, and this will be a map from the X4, which is the same as the product of the delta 2 and delta 1, to the C. And that's the end of the proof. So it's, I think it's now supposed to be very easy, right? Since we've done this arguments of this kind before, and you can only need to kind of verify this claim that this H indeed corresponds to the isomorphism, since we have this additional property for this joint lifting problem. And then you just notice that everywhere you have inner horns except the last step, and then in the last step you just have a left horn, and you can apply Giles lifting problem. Okay, so this is the observation. Yeah, but this claim that this is conservative is true not just for delta 1, it is true for any n. So, and this will be maybe another proposition, which is actually easy, because I can reduce this general case to some combinatorial statement that we already know. So again, let me assume that C is some infinity category. So C is an infinity category. And then the claim is the same as before. If I look at the functor from fun between delta n and C, to the fun from boundary of the delta n to the C, this is conservative. Now I assume that n is greater or equal than 2. So actually, the case where you need some separate proof with this Giles theorem is the case when n is equal to 1, and the case when n is equal to at least 2 can be reduced some combinatorial problem that we already know. So let's see how this works. Here, I notice the following, that this canonical map from the boundary of the standard simplex to the standard simplex, I can factor this. So let's take this map, and I can factor this map through the spine. Sorry, just the other way around. Sorry. You take the canonical map from the spine, right? And then you can notice that you can factor this map from the spine through the boundary of the standard simplex. Yes. Okay. So then we can consider the corresponding composition when you apply fun to the C. So then you get fun delta nc, which is mapped to the fun boundary of the delta n and c, and then this is mapped to the fun spine INC. Okay. And the combinatorial statement that I will use here is that the canonical map from the spine to the simplex is inner anodyne. That was one of the exercises and one of the assignments. So, but since this is an inner anodyne map, we know, again by special case of general properties, that the map from the fun delta n to the c to the fun I to the nc, so this is a trivial fibration. Okay, but this is so almost immediately give us the proof, right? Since if you know that this is this composition is a trivial fibration, well, in particular, any trivial fibration is a left to right fibration. So, for example, I say that this is left vibration. So maybe let's call this some name, maybe something like theta. So theta is a trivial fibration, and this implies that this map theta is, say, a left vibration. I can as well say right vibration, but just let me choose something. So let it be L. And we know, again, by the general properties of left and right vibrations, that they all conservative. So theta is conservative. But if the composition is conservative, then this first arrow is also conservative. So then so this is how we can reduce the proof of the case when n is at least true to the case to this combinatorial statement that the inclusion of the spine is inner anodyne. Okay. So now let's do the general theorem, which says the following. So I'm assuming that I have C, which is an infinity category, and I have some simplicial set, K. So then the functor from fun Kc to the fun K0c is conservative. So this is a general statement about conservative functors, and you can notice that if you go back to the beginning, if you know this statement, right? So if this is conservative in any such with any such assumptions, then immediately we see that the map Kc coincide with the fun Kc and maximal subgroupoid. So let's prove this. So for the proof, I'm going to use the skeletal filtration. So set Kn to be the n skeleton of the simplicial set K. Then, for example, we can notice that K0 is exactly the set of vertices. That's what we need. And K is the union, but a little bit formally, I can write this as the directed limit of the Kns. Okay, so now I want to take skeletal filtration, which gives me some push out, and apply functor fun to the C, to this push out, and get some pullback. So the pullback will be the following. I'll get fun K and C. This is mapped to the product of the fun delta NC. So, and this is for the fun Kn minus 1C, and the product of the fun so that's a pullback, which is the as I just explained, the the result if you apply fun from something to the C to the push out that you see in the skeletal filtration. And then here, if you don't have a product, right, you already know that for infinity category, each individual arrow here on the right hand side is a conservative functor. Right, so this is conservative. Yeah, and also here we use the following. So let's say that since fun delta NC to the fun boundary of the delta NC is conservative in a vibration, let's call this map maybe P. So P is a conservative in a vibration. Okay. So I'm using here that again, this is just special, one of the special cases of the statements, I think from the second assignment, that since you have this is mono, this is an infinity category, so the induced map on the fun is in a vibration. The fact that this is conservative we just proved in the previous two statements. And now to conclude that P is a conservative in a vibration, I'm using a very simple observation that the product of conservative functors is conservative and the product of inner vibrations is inner vibration. So again, that's a very simple observation. I'm leaving it as a little exercise. So that's this P is an inner vibration, and then since this is a pullback, I can also claim that this map here, and yeah, I proved on a week ago that the pullback of an inner vibration, of conservative inner vibration, is conservative inner vibration. So this map P prime, so thus map P prime is a conservative inner vibration, since this is stable under pullbacks. Okay. Yeah, so of course this makes sense for any n starting with 1. Okay, so this is the the first observation in the proof. So if you decrease this index by 1, you get a conservative inner vibration. But what we actually need is to go to the limit and claim that this limit is also conservative. And to do this, I can use Giles criterion for conservative functors. Namely, I need to verify that I have a solution of the following lifting problem. And maybe, I'm not sure that I have enough space here for this lifting problem. Maybe I just draw it here. Right, so I can look at the horn lambda n 0. So then this is included into the delta n. Right, so here I have this fun Kc, and below it I have fun K0C. I'm not going to draw an arrow at the moment because I want to use these Kns in the middle. So, but if I know that I have a solution, right? Well, I have this lifting problem with the assumption that the beginning, the first edge here is an isomorphism, right? Is an isomorphism here. So edge here mapped to some edge here, and this is supposed to be an isomorphism here, right? If such lifting problem has a solution, then I can say that this functor here is conservative by the Giles statement, one of the statements that I derived a week ago, and I call this Giles criterion for conservative functors. Okay, but here, of course, I want to look at these kns. So let me just include the general step from the kn minus 1c. Here there is a map fun kn c, etc. And then by the just the definition that the k is the directed limit of the kns, I'll get the canonical map from the fun kc to any such fun knc. So, and I can just, right, since I know that this first edge in this horn under this composition corresponds to an isomorphism, I can solve, for example, and I know, for example, that when this n is equal to 1, this functor is conservative, so fun k1c to the fun k0c, this is a conservative thing. And, for example, if I write k1 somewhere here, I'll get the lifting, and then the general step will be like this. Right? I just look at all the k's, all the n's, and I can notice that since I know that this is conservative, on the previous step I get an isomorphism here that corresponds to the beginning edge here, I know that there is a corresponding lift. By kind of Giles criterion for conservative functors, but in the other direction. So the conclusion is, I'm kind of diagram it there, but the I continue the argument here. So I get the map from the delta n. Since I can construct this lifting for fun k and c for any n, I'll get the map from the delta n to the inverse limit of the fun k and c. Right? Just combine all these maps that I constructed for each individual n. And then I just use that since this is a limit, I can put here as the colimit, so this will be the fun directed limit k and c. And this first argument is now just k, so I can identify this with the fun kc. So I constructed the solution of the lifting problem. That's enough to conclude that the functor is conservative. Okay. So first corollary from this is the following. If I assume that, well, as before, K is a simplicial set, C is an infinity category, so then, as the special case of this statement, I'll get that the map KC coincides with the fun KC, and then I take a maximal subgroupoid. So this is one corollary, and another one is just also completely trivial. It's just a slight generalization of this. So let now F from K to L be a map of simplicial sets. Such that F0, so that's the map on the vertices, is an isomorphism, or well, bijectional sets. So is a bijection. So then the functor from the fun K to the C to the fun L to the C is conservative. Just a slight generalization of the previous theorem. And indeed, there's nothing really to prove here, right? You just look at the corresponding square, right? You can look at the fun KC. This is mapped to the fun LC, right? But you also have a canonical maps from the first fun KC to the fun K0C. And then there is a map from the fun L0C, right? And so these vertical functors are conservative. You mean the direction is that in the other direction, right? Here. Here, right? Yeah, thank you. Yeah, so this is L, this is K, thank you. Yeah, so this is L, this is K. So this will be with this, and this is K0. Yes. But anyway, so the vertical functors are conservative. So the argument is so silly actually that it doesn't make that I made a mistake there, right? So the functors are conservative here because by the theorem, and also since we know that this map is a bijection from K0 to the L0, well here we have an isomorphism, right? But this means that since on the bottom have an isomorphism, these two functors are conservative, hence this functor is also conservative. Okay. So with this, I want to finish these applications of the JL's theorems, and I think I have something like 30 minutes. Oh, just want to tell you some several general ideas. Well, first of all, there's kind of some additional topics. I don't want to give them kind of numbers. Let me just say two words about the JL's model structure on simplicial sets. So I'm not going to prove anything. The proofs are actually, well, it's not so easy. Maybe I need something like another 4 or 5 lectures to prove everything here. Well, first of all, we can define the following. So let cat infinity, now but I'm writing infinity and not in the beginning, but kind of like this index. So be the infinity category of infinity categories, right? So how I can do this? Well, we can do the following. So objects are just infinity categories, of course. Now homes are defined like this. So you take the fun, say from C to D, and then you take the maximal subgroupoid. So this will be, well, since the C and D are infinity categories, we know that the fun is infinity category, so maximal subgroupoid is just some Kant complex. So at the moment, this is defined as a simplicial category. We have objects and we have homes, which are simplicial sets, well, in fact, Kant complexes, but this is simplicial category. And then, so homes are defined like this, and we get a simplicial category. So definition this infinity category of infinity categories is the coherent nerve of this simplicial category. And notation will be something like H cat infinity. Sorry, no. Just so this will be just a notation for the infinity category of infinity categories. This is how you construct this, right? So then, since it's an infinity category, there is H of this. They just one category, and you can, for example, verify the several. Well, you can take as a definition the following. So let's say again maybe a definition, an equivalence of infinity categories is an isomorphism in this infinity category of infinity categories. So it's an isomorphism in cat infinity, right? But since a notion of an isomorphism in infinity category can be completely determined in the homotopy category, I can as well just go to the homotopy category of the infinity category of infinity categories. Right, so this will be an equivalence of infinity categories, just another kind of analog of the equivalence of ordinary categories in this theory. So this is a kind of abstract definition that uses this infinity categories, but you can also say more explicitly, so remark, so F from C to D is an equivalence. This is exactly what you expect it to be. So means that there is map in the other direction, G from D to the C, well, such that if you look at the composition in one order, then this is naturally isomorphic to the identity on the C, and the composition in the other order is naturally isomorphic to the identity on the D. So natural isomorphism now we can define in two ways. You can just say this is an isomorphism in the category of functors from C to D, or you can just say, using the previous results, that this is a natural transformation such that every component is an isomorphism in D. So in this way we will get a notion of equivalence of categories. So then there are some technical results we can prove about this, but if you want to define a model structure about this, so at the moment this is defined. So an equivalence is defined if you talk about C and D being infinity categories. So now we can define. So let's take X and Y be any simplicial sets. Simplicial sets, and I want to kind of extend this definition to simplicial sets. So a map F from X to Y is a categorical equivalence. Categorical equivalence. So if we have the following, so if F, well, there are many definitions. So, but this is, for example, I think what Luris gave us a definition. If F induces bijection, from P0 of the fun YC core mapped to the P0 of the fun X C maximal subgroupoid. And that has to be true for any infinity category C. So for any C in infinity category. Okay. So, simple question for you. Do you see that if you take this definition of a categorical equivalence between simplicial sets, now assume that these two simplicial sets are just infinity categories? Do you see that the categorical equivalence with this definition between two infinity categories is exactly the equivalence of infinity categories? So these two notions, categorical equivalence and equivalence, coincide if x and y. No, not really. Well, here you look at this part. We defined these objects in the infinity categories, and simplicial homes are like this. But it means that, for example, if you take P0 of this thing, this will be exactly home in the homotopic category. This homotopic category. So they coincide because you can take this just one category, which is homotopic category, and apply Ioannidis lemma. So by Ioannidis lemma, this definition reduces to this definition when x and y are infinity categories. Okay, so without a proof, maybe I formulate this proposition, which is actually the proof is very, very easy. It's just another application of Ioannidis lemma. So let's say that f from x to y be a map of simplicial sets. So then the following are equivalent. So first condition that f with the upper star, this is from the fun yc to the fun xc. This is a categorical equivalence. Maybe just let me, for shortness, maybe write something that belongs to the cat equivalence. This will be the notation. So this notation is cat. Right, and this is for any C which is an infinity category. So condition number 2. Well, you take the same, but you restrict this to the maximal subgroupoid. So this is now homotopic equivalence of Kant complexes, HE for homotopic equivalence. Of Kant complexes. Again, this is supposed to be true for any C which is an infinity category. So condition 3, instead of taking maximal subgroupoid of the F upper star, you can look at the map induced on the homotopic categories. So when you look at this in the beginning, it looks like you're losing information on all the steps. So this is an equivalence of one categories, again for any C being an infinity category. And finally, condition 4, you apply P0 to the map induced on the maximal subgroupoids. So this will be from the P0 fun yc, maximal subgroupoid maps to the P0 fun xc, maximal subgroupoid, and this is just a bijection, of course. Again, for any C being an infinity category. So there are many ways, if you look at this fun, there are many ways to think, well, you can say that this is in categorical equivalence, or you can say this is just a bijection. I'm leaving this an exercise, but really this is a very easy exercise. It's just an exercise, again, in Yanadis lemma. There is nothing really infinity categorical here. Yes, and then there is another proposition, say categorical equivalences satisfy 2 out of 3 property, and categorical equivalences are closed under, sorry, not complex, under retracts. So they satisfy the properties that you expect from the weak equivalences in a model structure. Okay, so that's just briefly. Of course, there are some theorems that I'm not proving here, which is interesting and useful in the theory, but I just want to say that this is how you take this categorical equivalence and say that this is kind of a class of weak equivalences for some model structure. And then you define the, so next definition, categorical fibrations So we kind of try to guess the definition of fibrations in some model structure, but this is quite easy, right? Because we know that in any model structure, if you have already notion of weak equivalences and we have notion of cofibrations, and I want cofibrations to be just mono. So then the right complement to the trivial cofibrations, that's exactly fibrations. So hence I can define it as follows. So the notation is cat phi. So I take monomorphisms cell and intersect this with the categorical equivalences and then take the right complement. So this is the categorical fibrations. And so the theorem, which of course I'm not going, well, even if I have time I wouldn't prove this theorem, because for the understanding this as a really theory of categories, with enhanced theory of categories, this theorem is not that important, but just for completeness I can say that the classes where you take as weak equivalences categorical equivalences as cofibrations, you take mono, so cell with the bar, and as the fibrations, you take the categorical fibrations. So the clusters form a model structure on the category of simplicial sets. And this is called JL's model structure. Well, in my mind, it is not as important as, for example, understanding more precisely what our categorical fibrations are. And for this, I just formulate one proposition. So just the general theorem, and back to the categorical fibrations, I have proposition as follows. So let C and D be infinity categories. So then, if I consider a functor from C to D, then this is isofibration if and only if this functor F is a categorical fibration. So the logic is more or less the same as before. We took the notion of an equivalence of infinity categories and then kind of extend this to the all simplicial sets. Here we take the notion of the isofibrations of infinity categories and in the correct way try to extend this as a property of a map between simplicial sets. So, but unfortunately for the here for the categorical equivalences, that is very easy observation, just a Ioannidis lemma. This proposition is not so easy. It requires some proof, maybe half a page or a page of computations. But this is kind of, for me, this is a very natural statement because, for example, if you compare just the category of one categories, then isofibrations was exactly the fibrations in that model structure, kind of the natural model structure on the category of categories. And here you kind of just take isofibrations between infinity categories and naturally extend this kind of in the kind of. This statement, if you have any extension, this statement I think has to be satisfied to have a reasonable theory. Okay, so this is just a few words what other stuff can be done in this theory, and also I want to define the mapping spaces because this is related to what we proved today. So in the very beginning of the course, I was writing if I have an infinity category, I was writing something like home between two objects, between two vertices, and that was just all the edges. This is of course just a set. It's not a natural definition. The natural definition is the following. So definition. So let C be an infinity category. Let's take X and Y be two objects, so this is just vertices and C0. So the mapping space this is map CXY, and if you compare this with this map in the beginning of the lecture with large M, that was kind of temporary definition. This is a standard definition that is used everywhere. So this mapping space is defined as a pullback. So this is defined as the following pullback. Well, I have just a point X and Y, right? I can think about this as a vertex in the fun boundary of the delta 1 C, right? I can identify this with the product C and C, so hence this is just a point in the product of C and C. Right, so here we have this functor that we studied today, right, which is conservative functor. And then I take a pullback, and the pullback is by definition called the mapping space. Of course, if you consider special case, when this C is just the north of one category, this will be the standard home in C. There will be nothing topological about this thing, just a set. Okay, so but what we can notice here, I'm claiming that this mapping space is an infinity groupoid. So maybe here. So mapping space for any infinity category, for any two objects X and Y, this is an infinity groupoid or Kan complex. Since we know this is the same thing. Do you see that this is an infinity groupoid? Yeah, yeah. So this is conservative inner fibration. So then the pullback is a conservative inner fibration, but this is just the pullback is this map. So this will be kind of a conservative inner fibration. So this map to the point is a conservative inner fibration, but that exactly means that this infinity groupoid or a Kan complex. So kind of, as you can see, I can define this in the beginning of the course. But to understand that this actually something, that this, to say something non-trivial here, that this is a Kan complex, I need this theorem that I proved just today. So, this is a Kan complex. of maps between any two objects. And of course this agrees in the naive theory in the sense that if you take, say, maybe a proposition that says, again, C is in infinity category, X and Y as before are two objects, you take this mapping space, right, and then you obtain, and then you apply pi 0 to this mapping space. So what would you guess the answer is for this pi 0? Home? Which home? In which category? Yes. So this we can identify as a home in the homotopy category of C, from the X to the Y. So in this sense, this definition kind of agrees with our definition of a homotopy category, and so by pi 0, kind of the points give you the standard home, and then there's kind of all this other information that is hidden in the higher simplices. Okay. Unfortunately, I think I have only 2 minutes left, and I don't think I have enough time to say anything reasonable. Just maybe I finish with the remark that we can define, so say f from C to D is called fully faithful. For shortness, I'm just writing FF, right? Well, first of all, you can notice that actually this map F induces map on the homes, right? So that map induced on mapping spaces. This is not. I'm writing this like this is completely trivial, but it's an exercise in writing several pullbacks and understand that actually there is an induced map like this. F of X, well, F of Y. Well, even this claim that any functor from C to D inducing a map on the mapping spaces is not completely trivial. But I won't say this is fully faithful if this induced map is a categorical equivalence or just equivalence, but now I can say categorical equivalence. So that's the notion of a fully faithful functor. Now F is essentially surjective if HF is essentially surjective. And now there is a theorem that I was kind of hoping I can prove, but it doesn't look like it is possible. So that the functor f from C to D, this is again infinity categories, is an equivalence if and only if f is fully faithful and essentially surjective. So the standard theorem works, but it requires the developing more technique that we have at the moment. Yeah, and for the proofs, there are kind of two types of proofs of this theorem. You can reduce everything to the homotopy theory of simplicial sets, and for this kind of proof, you can look at the Caradon with a lot of details. And there is another proof that doesn't use any simplicial, any homotopy theory of simplicial sets, kind of maybe in some sense nicer because it's kind of self-consistent theory. You can find such proof in the RISC nodes on infinity categories. So they are quite different. Okay, so I think I'm out of time, so let me finish here.